All right. Let's go ahead and get cruising here. So on this bell work, we've got a few things happening. First things first, want to know how many solutions this has. 4x equals 2. We might need to find the solution, or we might be able to do it as it is. What do we think? If I just wanted to solve this, 4x equals 2, what do I need to do? Or 4x equals 2x, excuse me. Yeah, if I wanted to get my x's together, I could subtract 2x from both sides. Since we've got that equal sign, as long as I do the same thing to both sides, I can do whatever the heck I want. That's going to give me that 2x equals 0. So from there, can we tell how many solutions this is going to have? Say it a little louder. Still can't hear you. It's not infinitely many. Finish solving it then. What do we get if I divide by 2? 0. Is 0 a number? How many numbers is 0? It is one number. 0 is a number. If x equals 0, 0 is our solution. If my x's cancel out, is when we would have 0 equals 0. So like if this wasn't 4x, but this was 2x, that's when we would have an infinitely many situations. Solutions, not situations. 7 o'clock. My brain's also not good. So x equals 0 means there is a solution. There's one solution. It happens when x equals 0. So we have one solution here. If I had something like x squared equals 4, that's when we would have our 2 solutions, because it could be positive 2 or negative 2. Infinitely many is our 2x equals 2x kind of situation. Our 0 solutions would be like x squared equals negative 9. It doesn't give any real answers. It's imaginary only. That was random. Okay, number 2 is using the patterns we were looking at yesterday with our difference and sum of cubes. So this is the special patterns, and if you need a copy of them, they're on page 5 in the notes. So for A here, how am I going to rewrite this into our cubes that we can use for our special pattern? I want to be able to write this as 2 things being cubed. So what cube gives me 27x cubed? 3 and x. So if I have 3 cubed, I get 27. If I have x cubed, I get x cubed. So 3x cubed gives me 27x cubed. What cubed gives me 8? 2. So that means looking at that special pattern that we have, this is my A term, this is my B term. So my 3x and my 2. So we make sure that we use the pattern that had the minus on it. And we can write this into our factored form, where we're going to have our 3x with that same sign and the 2. And then we'll have our 3x, that first term, squared. It's going to give us 9x squared. The opposite sign, 3x times 2 gives us a 6x. Always positive. 2 squared gives us 4. So following the special pattern on page 5. So if you forget where these are on page 5. part B has one other thing we need to do. What we need to do on part B? Bless you. We have a GCF here. We've got a greatest common factor. We need to divide all these pieces by 3 so that I can take out that greatest common factor of 3. Absolutely right. So I could 100% rewrite this, and I haven't changed anything, by putting the 3 in front and having this be x cubed plus what? 1. Now I've got a perfect cube and a perfect cube. 1's a perfect cube. So we can again use our pattern. This one's going to be the plus option because this one's a minus. This one has a plus. Oh, snap. So the 3 just hangs out in front. He's not a part of it. I mean, he's a part of the answer, but he's not a part of the factored. Where we'll have our x with the same sign and 1, because 1 cubed is 1. Our a term, that x squared, opposite sign, 1 times x is x, plus 1 squared is 1. So following that special pattern, being able to use that, substitute in the pieces we have. When x is cubed, we get x cubed. When 1 is cubed, we get 1. So we had a term being x, our b term being 1. Questions on those two, since that's what we did yesterday. So these are our 2 final answers there. These are not well aligned, but that's good. All right, number 3, our final question up here is to solve this system. Barrier here, just want to use this space. What the heck are we going to do to try and solve this system? More specific. Sub in what? Oh, set them equal. I heard sub in. I have 2y equals equations. I know y equals this. I know y equals this. So I want to know when y equals y. Because I want to know when this equals this. So I'm going to take this and substitute it in place of the y. I'm going to set these 2 equations equal to each other. So we're going to take the fact that y equals this piece and substitute it in place of that letter y. So we can write this as x squared minus 6 equals our 2x squared plus 5x. I know I'm hysterical. How do I solve this? Definitely a choice, but it's not going to be the easy way if we do minus the 2x squared. If we minus the x squared. If we always move the smaller one, because 2x squared is bigger than x squared, if I always move the smaller one, I will have the fewest amount of negatives. So I would like to have my x squared still be positive, so I'm going to move my smallest x squared. So I'm going to minus x squared on both sides. That leaves me with minus 6 equals 2x squared minus x squared gives me just 1x squared plus 5x. What should we do next? We are trying to solve, and I have an x squared. What needs to be our goal? Just don't pull the door shut all the way behind you or you'll get locked out. Hello, hello. How you doing, dear? How are you? Cool, cool. All right. All right. When we have an x squared and we want to try and solve it, what does it need to equal? I am being a clue. What does it need to equal? I heard it. It's very quiet and very whispered. I need it to equal 0. We have an x squared. Means I'm going to try and factor the dang on thing. So I need this to equal 0. I already have my x squared positive, and I would like my x squared to be positive. This is so much easier to factor if the x squared is positive. Oh my gosh.
Add 6.
So we're going to add 6. Absolutely right. I'm going to add 6 to both sides. That's going to give us that our 0 equals x squared plus 5x plus 6, but I still don't have an x equals. Oh my god. What do I have to do now? So much work. We need to factor. I'm going to give us a little bit more space. So I want to get all the way down to an x equals. I have x squared. I got to try and factor this or put it through like the quadratic formula, but So we could, but it's going to be a whole lot easier to factor this sucker. A times C at the top, B at the bottom. A is 1, C is 6. So top number is going to be 6. B on the bottom is 5. What pair of numbers do we know that multiplies to make 6 and adds to make 5? 3 and 2. Now we can absolutely put this through our full factoring, through the box, through the splitting in the middle, bottoms up, by grouping, whatever method you got. Or we can go, hey, wait a second, my A was 1. Shortcut mode. The 0 equals, and we just take our x with the positive 3 from the frame, and my x with the positive 2 from the frame. Ta-da! Factors. So only when our A value is 1 can I just take the fact that, hey, positive 3, positive 2, positive 3, positive 2. So then what we need to do to find our solutions here is I need to take and get my solutions for these two factors. What do I do to find my solution for this factor? Set it equal to 0. So for each of these factors, I'm going to set them equal to 0. That is why they roots, solutions, zeros. X-intercepts. Factors of the whole x plus whatever. Root is when we get our answer. So what are our answers here? What are our solutions for x? -3 and -2. 6 equals -3. X equals -2. Now we should take these back up and plug them back in to get points as ordered pairs to get to solutions. But holy cow, we actually need to get to some content today. Oh my gosh. It's a long problem. But we got it most of the way there. Mostly I think just remember this bit. Questions on these ones? Okay, because we are going to work in our notes packet today. We are going to look at page 6. At the very bottom has this exact picture. And I'm going to talk us through it. We're going to be looking at a different kind of factoring option. Because we've only done factoring for like quadratics or cubes when they were in that very special pattern. All right, so I even mentioned this when we were looking in the bell work for how to factor that x squared. We could do our bottoms up, we could do the box, we could split the middle, we could factor by grouping. Factoring by grouping. So we've seen factoring by grouping before. We're just going to do it a little bit more specifically with our polynomials here. Sometimes when we are factoring these guys, it doesn't work any other way. I don't need to do like super crazy things to try and make my factoring happen. If it doesn't factor, it doesn't factor. But sometimes it does, just in a different way. So when we're going to do our factoring by grouping, we need to have two pairs of things that I can see GCFs in. So it's not going to work every time, which is why it's one of those things that we kind of go, it's good, but it's not perfect. And it's giving us this example down here that's very, 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 very lettery. I'm going to zoom it in on because it's very, very much at the bottom. So what we do when we're factoring by grouping, we have this polynomial. So this might be 4x cubed plus 3x squared plus 6y plus 4y. Whatever. What we can do is we can break them up into pairs. We look at this thing and we go, ew, this is really, really big. I could say, well, what if I look at just those two pieces? Oh, look, they have something in common. And what if I look at these two pieces? Oh, look, they have something in common. These two things just have x's. These two things have y's. So what we do is we break them up into pairs. I did not recommend it. You got knocked out, my dear, because I didn't hear it. So when we're doing factoring by grouping, what we do is we group them. We get to pick which ones go together. So they put together the two things that had x's and the two things that had y's. Then they're taking our GCF out of each of them. So these ones I can take an x out. These ones we took a y out. So taking our GCFs out. This is at the bottom of page 5, or page 6. I'm just zoomed in real far because it's at the very, very bottom. So this was taking out our GCF of x here, and this is taking out our GCF of y. Then what we're doing is we're taking out this chunk right here is acting as another GCF because they're exactly the same. I can take this piece out as its own GCF. So how I took this one x, or these two x's, and it became 1. I'm going to take these two a plus b's and have them become one factor. Any of the leftover guys become their own factor. I did not realize I could zoom that in like that. Okay, there we go. So we're going to practice with this. It's the same process that we did with quadratics. We're just not going to need to use the x frame to split that middle term into two different pieces. It works the exact same way. I'm not super fan of the fact that it's on the next page when we do our practice of it. So here's the first one we're going to do at the top of page 6. So this one has two different kind of letters, and that's okay. We can do this. So what we do when we're factoring by grouping is I'm going to take and make two pairs. More often than not, it'll work in the order we give it to you. So I'm going to break these two off into their own pair, and I'm going to break these two off into their own pair. So I'm going to rewrite this with some parentheses in it. So I am going to rewrite this problem as 2uv plus 6u in one set of parentheses. Oh, sorry, I will zoom out so it's not on crazy person zoom. And I'm going to also put my 5v plus 15v. When we're splitting these up by grouping, we always want to have a plus in between right here. If this guy has a minus sign, pull it in right there. So we always want to put a plus in between our parentheses. But I do this. Paranoid now. So then what we want to do is we want to look at each of these pairs and see what I can take out as a GCF. What do we have as a GCF on that first pair? 2 and u. So I can take 2, there we go, 2u out of this first pair. What's left over when I take 2u out? V plus 3. Then we're going to do the same thing looking at the right-hand pair. What do those ones have in common? 5, just 5. So we're going to take out a GCF of 5 over here. So we're going to have our 5. When I do that, what's left over? V plus 3. So what I see is that I have the same exact term, and this only happens if this were. this same exact term right here, my v plus 3, I'm going to treat this as a new GCF so that I can take this out. So how we took our 2u out here and it went in front and made new parentheses, hold these in. I'm going to take this v plus 3 out as its own GCF. So I'm going to write that guy first. V plus 3. What that's doing is that's taking this guy and this guy and saying, hey, that's my GCF right there. So then we look at the pieces that are left over. What we have left over is a 2u and plus 5. So our leftover bits, these guys that were in front, they make their own factor. I'm going to zoom it back out to the whole view. Just because it was very small on here. I don't know why this is all on the same page, but it is. Questions on what we did right there? Because we're about to write out step-by-step instructions, and then we're going to practice it some more times. So this kind of list right here, we're going to use to write out our instructions of steps we just did. So what we do is we take our polynomial that we're given, and we're going to split this into two different polynomials. When we're doing our factoring by grouping, we split it up into our two pairs. Could have more, but we're only going to give you two. Then what we do is we found our GCF of each of those groups, completely independently from each other. So we find the GCF of both groups. Then we put our matching factor. We put our matching factors. It doesn't really matter which one's first. I find it easiest to take this thing that matches and make it be the first, but you don't have to. It doesn't matter what order we put our factors in. And you can combine whether you think of these as the original GCFs, if you think of these as what's left, whatever these leading coefficient things are, these guys are leftover bits to form our second factor. So we're going to combine our either the first GCFs or the leftovers, however your brain thinks of it better, to form the second factor. It's exactly what we did at the top. We break it into pairs. We find our GCFs. We put this factor first, and any of our leftover guys, those original GCFs, the 2u and the 5, those guys make their own factor, and we are in factored form. And then we're going to go practice this again, because these are weird. But there's some times that this is the only way that we can factor it. So this works for our quadratics as well, but this is one of those things that does work for polynomials. Okay. I don't like these being so low, but whatever. So page 7, we're looking now just below it. We've got A, B, C, and D. We're probably not going to get through all 4, but we can at least get started on most of them. We've got about 10 more minutes. We can do this. So looking at this first one here, A, our first step is to split this into two different pairs. So I'm going to take these two pieces and group them together. And I'm going to take these two pieces and group them together. So when I rewrite this,
I'm going to write this as my x cubed plus 4x squared. We always want to put a plus in between. I promise it really does help. And then I'm going to put these two pieces together. My minus 6x and minus 24. So whenever we're setting this up, we should have a plus in between. Otherwise, we're going to run into issues with signs. So then we look at each of these pairs individually. What can I take out of x cubed and 4x squared? X squared. I can take x's out, absolutely, but I can take an x squared out of both of them. So we want our greatest common factor. So I can take an x squared out. When I take x squared out, what am I left with here? X plus 4. And again, if I was to distribute that out, I would have exactly what we had above. If I went x squared times x squared times 4, I get exactly this. Great way to kind of spot check. What about on this pair? My minus 6x and minus 24. Negative 6. And that's one of the reasons we want that minus sign tucked in there, because if I didn't take the minus sign in between, it would be really hard to remember that that was negative 6 that we needed to take out. And that's going to leave us with x. So if I take the negative 6 out of 6x, we're left with x. And what? Plus 4. Negative 24 divided by negative 6 gives us a positive 4. Once we get to this point, we can notice that we have a plus negative 6, and we can just drop the plus right here. Totally cool if you want to leave it. That's awesome. Now that I have a factor that match, these are supposed to match. If these don't match, it didn't work right. We stop right there. All right, so now that we have those pairs, thank you, dear. I'll take it. Now that we have those pairs factored out, I can go ahead and split this apart. I have a new GCF that we can take. This x plus 4, I can write that in the front. So what I'm going to do is I'm going to say, hey, this guy matches this guy. I'm going to take that out as its own GCF. So I can put that in the front as an x plus 4. Then I have all these leftover guys stuck. So I pulled these guys out, and my leftover pieces are going to fall back together. So I'm going to have my x squared and a minus 6, and those guys are going to make their own factor. So we're going to have our x squared and our minus 6. And we took this polynomial down to a factored form. There may be times when we do this that we could factor again. Because if this was, I don't know, like a 4 or a 9, we would then have a difference of squares. Which we have what? And I could get this all the way down into a fully factored linear form. Absolutely a thing we could do. Yes, dear? That would be our pieces with x squared with minus 6. So when I take this plus x plus 4 out, my leftover bits kind of fall together. I will change their colors so they match where they came from. So here's our x squared from that leading coefficient and our minus 6. That guy and that guy. I take that x plus 4 out as its own GCF, and everybody else just kind of falls together. Okay. Any one question. Any other questions on that one? I love questions. Questions are my favorite. Okay. Let's try the next one. These are weird. They are awkward. It's a thing. I'm sorry. One of those things. So our first step is to break these up into pairs. So I'm going to take my first two pieces and make one pair there. And I'm going to take my second two pieces and I'm going to make one pair there. We want to make sure we have a plus in between. Since there is a plus in the middle, we are good to go. So I'm going to break this up into 2b cubed minus 4b squared. And we're going to have our b minus 2 as its own pair. Looking to find GCF of each piece. What do we have as the greatest common factor on this pair over here? The 2b cubed minus 4b squared. What do they have in common? 2b squared. 2b squared. That's an old song. I could take 2b squared out of this factor and be totally fine. If I do that, what's left over? B and minus 2. What is the greatest common factor of this side? What do they have in common? 1. Good catch. Yes, this is when they try and trick us. It's not that they don't have anything in common. They have 1 as a common factor. It's not something we use often because why would I need to multiply by 1? It doesn't change any dang on thing. But when we're factoring, it comes into play because I can't just skip those terms. So if we don't see a number or a letter they have in common, it's a 1. And again, if I was to stop here and like redistribute all my stuff out, we would get exactly what we started with. Then what we're going to do is we're going to take the fact that we have the exact same piece here and here to pull this out as its own little factor. So we're going to put our b minus 2 as its own factor. That means these two pieces are gone, and those last pieces, the ones that are left over here, my 2b squared and my 1, are what make my other factor. So when this guy gets pulled out to the front as a GCF, anything left becomes our remaining factor. So our factor here is going to be our 2b squared and the plus 1. That's coming from that guy and that guy. Questions on that one? Okay, let's do C, and we'll stop there. So there's nothing wrong with D, but we have 4 minutes. So again, we start by breaking things into pairs. My 12a cubed minus 9a squared, I'm going to make that be a pair. My 4a minus 3, I'm going to put those guys as a pair. So we're going to rewrite it, just breaking things up into smaller chunks. It's a lot easier to look at if I don't have to look at all 4 things at the same time. So we split them up into pairs. Looking at just this left one, this green one. 12a cubed minus 9a squared. What do we have as a GCF? What do 12 and 9 have a 3 as a common factor. They're both divisible by 3. So I could write this as 3. They both have a's, and in fact, the smallest a that they both have is an a squared. So I can take that out as our common factor. And that's going to leave us with a 4a, 12a cubed divided by 3a squared. 12 divided by 3, 3 minus 2. So we subtract our exponents. And if I divide my 3a squared out of my 9a squared, well, a squared divided by a squared, those guys cancel out, and I'm left with 3 divided by 9, which is 3. So if I take my 3a squared out of that first factor, we're left with our 4a minus 3. So we looked at this first factor. What is the greatest common factor of 4a minus 3? 1. Again, they don't have any other factors in common. They're allowed to do that. So our greatest common factor here is going to be that 1. Which means when we're trying to write this in our factored form, we can take the fact that this guy and this guy match to pull it out as its GCF. So we can write this as our 4a minus 3. And then our leftover bits make their own factor. So we're going to have our 3a squared that's going to come on down. And we're going to have our plus 1 that comes on down. So we've gotten ourselves into the factored form. Okay, so when we're trying to factor by grouping, we break them up into pairs.